Hi, my name is Cristiana Narach, and today I'll be presenting my findings for my Lab 4 Rope Spring Lab. The objective of this lab is to analyze the motion and the forces involved in a spring mass system that was oscillating in two dimensions, the x and the y direction. How are we going to do this? By using Tracker, we're going to extract the position data of the mass attached to the spring, and then, using those points, we're going to create a simulation of the motion on GlowScript. We can see a preview of my results of my computer model on GlowScript on the right. Why is this lab significant? Well, it will help us visualize how energy is conserved throughout the entire motion and better illustrate the correctness of Newton's law of conservation of energy. The main physics principles used in this lab was number 1, the momentum principle. Then we used the energy principle, which is that the total energy is equal to the gravitational potential energy plus the spring potential energy plus the change in kinetic energy. Also, we use equations such as mass times gravity times height to calculate the gravitational potential energy. And to calculate the spring potential energy, we used 1/2 k sub s, which is the spring constant, times s squared, which is L minus L naught squared. We also used the equation for spring force, which is negative k sub s, or spring constant, times L minus L naught times L hat. We use Tracker to track the position of the mass attached to the spring over each frame. To the right, we can see a graph of the y position over time of our mass. We use the equation t is equal to 2 pi squared of m over k to calculate the spring constant. First, we calculated t, which is the period of oscillation, which was 1.52 seconds. We calculated this using the graph on the top. Then we isolated k to find our spring constant, which was 6.87 newtons per meter. And then we used the equation L minus mg over k to find L naught, which was 0.127 meters. Now for our coding. First, we inserted that the mass of the ball is 0.402 kilograms. Then we used Tracker to calculate the initial position of the ball, and we know that the initial velocity of the ball is 0 because it starts from rest. Then we stated that the gravitational constant is 9.8 meters per second squared, and our spring constant and L naught comes from what we previously calculated using these formulas. Then, for our loop, we defined the initial energies, and then we defined the gravitational force. The spring force was calculated using the equation we previously stated in the equations that we will be using in this lab. And then our F net is just the sum of the spring force and the gravitational force. Then we use the momentum principle to update the velocity of the ball and the position of the ball after delta t. And then we updated the spring position as it stretched and compressed throughout the motion. Finally, we use the energy principle to calculate delta kinetic energy, delta gravitational potential energy, and delta spring potential energy. And then we set total energy equal to the sum of all of these. These were my results. The blue ball represents the computational model ball, and the red ball represents the one that follows our Tracker data. We can see that they follow a super similar path. To the right, we can see the two graphs that we got from our computer model. The first one is a change in energy over time. The orange line represents the change in total energy, which remains constant. The green line represents the change in spring potential energy, and the red line represents the change in gravitational potential energy. Finally, the blue line is our change in kinetic energy. This bottom graph compares our computer model position with our Tracker position, the blue being the computer model position and the red being the Tracker position. We see some discrepancies in the amplitude of both of these, mainly because our computer model does not account for drag force, and there is room for some slight human error in Tracker as I tracked the position of the mass. In future labs, it would be useful to actually account for the drag force in order to make this result more accurate. Finally, let's analyze. For our model system, is the energy principle satisfied? Yes, our change in total energy is modeled by the orange line we can see here. We can see that it is 0 and constant, meaning that throughout the entire motion of the ball, energy is conserved. Now let's compare two separate estimates of the period of oscillation, one for the x position data and one for the y position data. For the x position, it was 1.646 seconds. For the y position, it was 1.519 seconds. The difference between them was 0.13 seconds, and shows that it takes more time for the ball to cycle in the x direction than in the y direction. The y accounts for the vibration of the spring, which means its compression and stretch, and the x for the swinging of the spring.